For those of us who are excited by the idea of space travel, we recently got some good news. NASA is looking into the idea of sending humans to Mars as early as the late 2030s. That means ideas and hardware designed to get us to Mars is now being ramped up to meet this challenge. But if you ask anyone who has ever been involved with the Mars mission, they will tell you that successfully landing on or orbiting Mars is incredibly difficult. In fact, of the more than 40 missions that humans have previously sent to Mars, less than half have been successful. One of the major challenges that face NASA researchers is how to deliver heavy equipment and people safely to the surface of Mars. Popular movies and science fiction articles make landing on a planet look easy, but in fact, that is one of the hardest elements to achieve. There are a host of aerodynamic and physics issues that engineers need to overcome. First and foremost is decelerating a spacecraft, traveling many times faster than a bullet, and allow it to gently land with precision onto another planetary surface hundreds of millions of miles away. To date, the maximum weight we have landed on Mars is about 1 ton, but when humans arrive, we'll need to land 15 to 20 tons onto the surface. The only way to accomplish this feat is to innovate and come up with a new strategy. A small group of dedicated NASA engineers, researchers, designers, and craftspeople are currently working on making a safe entry into the Mars atmosphere possible. The technology is called HIAD, for Hypersonic Inflatable Aerodynamic Decelerator, and it promises to redefine how we deliver spacecraft to Mars and other planets with atmospheres. Coming up on this episode of NASA X, we will take a look at the difficulties associated with landing on a planet like Mars and see how the NASA HIAD team plans to overcome the tremendous challenges faced with landing there. We will also visit the labs and partner companies who are helping to build HIAD and see firsthand what true innovation looks like. Entry, Descent, and Landing, or EDL, is one of the most challenging aspects of any lander mission. That's because landing a spacecraft is hard. Whether you are landing it back here on Earth or on another planet like Mars. Although it's not easy on either planet, Earth's atmosphere does offer more help to slow down a speeding spacecraft. This is because our atmosphere is dense compared to Mars. When a spacecraft flies through an atmosphere, aerodynamic forces act upon it to help slow it down. The drag that is created on the craft allows it to decelerate to the point where subsonic parachutes can be deployed, or in the case of the shuttle, where a guided landing could occur. The same can't be said for a Mars landing. The Martian atmosphere is very thin and much different than Earth's. In fact, the densest portion of the Martian atmosphere is only about as thick as our atmosphere is at 100,000 feet. As a result, a spacecraft flying through the Martian atmosphere does not generate as much drag, so it cannot be slowed down as quickly as it could back on Earth. For most laypeople, 2 immediate thoughts may come to mind about how to slow a craft at Mars. The first is to use rocket propulsion. In theory, this is a good plan, but in actuality, the amount of fuel needed would be enormous. One NASA study determined that landing 40 tons on the surface of Mars would require over 60 tons of rocket fuel. The other thought is to use giant parachutes. However, this much mass would require a cluster of parachutes, each the size of a football field, to be deployed while traveling more than 2 times the speed of sound. So to the HIAD team working on this problem, the solution is clear. Use a larger vehicle so that the Martian atmosphere slows us down higher up in the atmosphere. Previous missions have used the atmosphere to successfully slow a craft, but the mass and entry speed of these spacecraft, coupled with the thin atmosphere, limited landing areas to only the lowest elevations on the planet. In fact, currently only 40% of the Martian surface is accessible for 1-ton payloads. Clearly, these are major issues that must be overcome before we can send larger payloads and eventually humans to Mars. So how do we overcome all these obstacles? Here at NASA, a group of engineers and researchers are working on that exact problem, and they have come up with a solution that looks like the most viable option available to us. They call it HIAD, or Hypersonic Inflatable Aerodynamic Decelerator. Here is Dr. Neil Cheatwood to explain.
If you look at how we get to Mars now, we're using the technologies that we developed back in the 60s and 70s for Project Viking. That was the first time we successfully landed on Mars. Way back when, in the 60s and 70s, Project Viking had a technology development effort, and that's where they developed a thermal protection system. It was known as SLA, Super Lightweight Ablator 561V for Viking. And we've been using that for every successful mission to Mars up until our most recent venture, the Curiosity rover. So we had that TPS that was heritage from way back when. The disc gap band parachute, the supersonic parachute, was developed under the Viking program. And we're still using all these things. We're still flying the same aeroshell four-body shape that we had from Project Viking. So we've been living off of that heritage, off of that legacy. But with the Curiosity rover, we basically landed as much mass as we possibly can at Mars, at least at that altitude. If we tried to land more, we would end up hitting the surface before we achieved all the sequence of events that we had to achieve in the timeline. If we wanted to land that same rover at a higher altitude, also we would run out of time. We would hit the ground before we finished everything we needed to do. And so that was our motivation when we started looking at Irby, the first Irby mission. And so what we had done, one of the guys that was involved in this had done some research and seen a concept that the Russians were developing. And they tried flying this inflatable aeroshell, something where you could deploy something bigger, and a larger drag device lets you slow down faster, so you can either land that same mass at a higher altitude, it just naturally falls out of the equations, or you could bring in more mass and land it at the same location. So we were looking at deployable devices. The Russians were looking at this inflatable aeroshell, but they covered theirs with an ablative thermal protection system, and we were concerned that maybe that wasn't the way to go. And so we started looking at one where we could just make it bigger so that we could keep the heat rate down lower and not use an ablator. But with the human scale, now you want to land 40 metric tons, or certainly at least 20 metric tons. And it's like, holy cow, how are you going to do that? Let's talk some numbers. With the Curiosity rover, that mission, the Mars Science Laboratory, is the largest aeroshell we've ever built. So the aeroshell is what protects us when we go through the atmosphere. It's a cocoon for our payload, for our science. So that structure, that protects that, and to protect the structure, we have to have that heat shield that protects us. That aeroshell for MSL, Mars Science Laboratory, is a little over 4.5 meters in diameter. Biggest one we've ever built. It's bigger than Apollo, bigger than anything. It's a big aeroshell. Even with that large aeroshell, what it contains within that rover and all of its experiments are so heavy that we can't decelerate fast enough to reach the higher altitudes of Mars. In fact, the best we can do with that system, we can't even get to what was the Mars sea level. So we're landing below what was the Martian sea level. Where it ultimately landed is about -1 kilometer, so a kilometer below that sea level location, because it's just so heavy. If we had a larger aeroshell, then we could decelerate that mass sooner.
That larger aeroshell could be a HIAD. Because the launch vehicle can only physically accommodate a certain size payload to fit inside the fairing, engineers believe that an inflatable aeroshell is the best answer to get larger mass items onto other planetary surfaces with atmospheres. The basic concept of a HIAD is pretty simple. The payload is placed in the center, surrounded by a group of rings, or tori, that look very similar to large inner tubes. The tori are stacked in such a way that different diameters will be stacked one on top of each other and strapped together. Then, a flexible thermal protection system is placed around them to create a more smooth and heat-resistant surface. The materials used are incredibly strong fabrics like Xylon and Kevlar, but can also easily fold into the rocket shroud. Once inflated, these craft can become stronger than steel and handle tremendous loads.
Well, one thing that maybe can give people an idea of how structurally strong and durable these inflatables are is that a 15-meter design of an inflatable aeroshell is designed to take a load for about 300,000 pounds during entry. So 300,000 pounds is approximately 100 cars. So if you think of stacking 100 vehicles on top of this fabric structure is very impressive. That structure this made out of cloth and woven materials can take that kind of load.
Once the craft arrives at its destination, the HIAD will inflate to enter the atmosphere. All of these strong, heat-resistant materials will act together to keep the payload safe from heating, while slowing the craft down long enough to land at virtually any location. This device has already undergone spaceflight tests and has proven to be incredibly successful. It has been flight tested twice, most recently on a test called ERV-3. ERV-3 launched in 2012 from the NASA Wallops Flight Facility on Virginia's eastern shore. Although it was a relatively small test, the data that it produced gave the team the confidence they needed to continue exploring this concept. ERV-3 entered Earth's atmosphere at Mach 10, 10 times the speed of sound, and successfully survived the heat and forces of the journey. Temperature readings recorded on this suborbital test were as much as 1,000 degrees Fahrenheit, and the device experienced forces up to 20 Gs. This test opened the doors to larger missions and the opportunity to construct larger HIADs. Up next, we'll see how a new HIAD article is custom-made by hand in a unique facility in California. When you think about building a craft to travel to other planets, you may think about men and women in pristine buildings coming up with designs and concepts on the computer, then high-tech machines and tools used to help put them together. In truth, that is how many craft are built, but in these early stages of HIAD testing, the places where these devices are being constructed look more like workshops than pristine clean rooms. And although the men and women working on this concept are using computers to aid in their development, there are also skilled craftspeople that are putting together these devices just like a fine tailor may put together a suit. Here in this nondescript building in California, you can see how these fabric pieces are put together.
They're tailored. It's an art form. I mean, you can't just plug it into a computer and spit it out and make this. There's a hands-on, huge hands-on influence, and that's mostly where my side comes in, communication with how to build these things, figure out how to get the finished product we want from materials we've never worked with before in our lives. There's the major components to the Taurus. We have the braid, which is the outer material you see with the crisscross. We have the liner, which is inside of that, which is the seal. It basically keeps the air from leaking out. And then we have an adhesive we use for coating and for bonding all the pieces together. On the table, everything's laid out flat, so it's not in this curved shape when we're building it. It's straight in a tube. We take all our measurements straight. We use squares and basic tape measures, rulers, mark with a permanent marker and make a cut. With the ends, it's like the end of a t-shirt. If you cut it, the ends will fray. We have to kind of doctor the ends up to make sure that they don't fray and unravel, so we can consistently have the length we wanted. These liners can be 200 feet long, and there's a line that I've drawn that I have to keep, and I just walk along and cut this line, but because there's no machine that's out there to make a cut that long. So and at this stage it's all handwork. So we basically piece it together, and if the piece isn't wide enough, like the liner inside the torus consists of 3 different pieces. It's got, because the material is not wide enough to go all the way around, we have to put seams together to get the size we want. So I have to not only cut the panels and line them up, then I have to butt them up and then glue the panels together with an RTV adhesive we use. The yellow and red one are both the same construction. The yellow one hasn't been coated yet, so it's built to the right shape, but all the pieces haven't been tied together.
When the braid's finished like this is uncoated, so if you take the pressure out of this article right now, the braid will get completely disorganized, and the gas barrier inside the braid would actually become disassociated with the outer layer, so when you went to inflate it again, the barrier would probably wrinkle up inside, and you'd have localized elongation that would exceed the capabilities of the material, and you'd probably spring leaks in it. And also the braid itself would tend to open up gaps. So before we can deflate it, we have to coat it, and we use this high temperature silicone coating. It's a RTV that we put on it. It helps organize the braid, and it also, we push it through the material so that it adheres to the gas barrier on the inside, so those stay locked together in a matrix.
After putting together these tori, the next step is to begin testing. Up next, the article is placed inside a hydro rig, while engineers test the HIAD's ability to withstand high pressure.
Yesterday we were performing a test to prove that the article can take a certain amount of pressure inside of it. I have to work around this thing. As the pressure gets increased in them, with air inside of it, if it pops, it's like a balloon. You pop a balloon, and even though it doesn't have much pressure in it, you pop it makes a loud noise. There's this energy going somewhere. If you take a water balloon and put it underwater and pop it, the only thing you're going to see is you're going to see the outside of the balloon just kind of disappear. You're not going to have any of this effect or movement. So what we were doing is we were testing the article to a high pressure that we calculated would be good to, but we don't want to test it with air, because if it did pop or rupture or have a failure, then it would be like a balloon on steroids. So by putting it underwater, filling it with water, taking it to a pressure which is higher than we would ever operate it at, we have that cushion and that comfort level. I can stand next to it and know that it's safe to operate and be around.
So as lead for the inflatable structures development, I'm working with a group of engineers. We're doing analysis work to structurally analyze the design to make sure it can take the loads that are being applied. We have to also look at the thermal properties of the material so it can withstand the heating environment. And we're also doing a lot of material testing. So everything from testing from the strength of materials to being able to withstand the temperatures.
The team has good data about these smaller tori, but if we are to use this concept to eventually land humans on Mars, we must get these sizes much larger.
One thing about soft goods is they're hard to characterize. We have a lot of analytical models that we have pretty good faith in now that we've developed over the course of the HIAD project. But still, as we make these large jumps, there's not a lot of faith in them. And so the only real way to get data is to build these things and test them.
The tori stack that is being manufactured here in California is the structure, the interior piece of the HIAD. But the flexible heat shield, the external piece, is being designed and built across the country in Dover, New Hampshire. At this facility, a small team is developing the process that will be used to sew together the cutting-edge materials used on the exterior of the HIAD structure. Because the external shielding will see the highest temperatures, it must be made from materials that can withstand the massive heating environment the HIAD will encounter.
Flexible thermal protection system is part of a re-entry system that could be used to bring things back from the space station or ultimately go out and provide larger payloads out to Mars. It incorporates a thermal protection system outer layer with an inflatable interior portion which provides the shape and stability. The fabric is silicon carbide, which allows it to take the high heat loads, unlike other materials that we've tried past. The insulating layers are carbon felts and an aerogel material. They're backed up by a gas barrier, which prevents any gases flowing through the entire system. So the highest temperature rated materials on the outside, and then insulators to prevent the gas barrier from overtemping.
Although this material is incredibly resistant to heating, it is somewhat challenging to manipulate in the construction process. That difficulty has forced this team to come up with innovative proprietary sewing and manufacturing procedures to outfit the HIAD. Once the outer shell is married with the internal structure, you have a very strong, heat-resistant cover that can be folded and packed to fit within a rocket shroud. And the combination of all the parts together now make flying to Mars and other planets with atmospheres much more viable.
This technology is not just an incremental advancement in our entry capabilities for NASA. This is actually a leap. We are actually making a big change in what our capabilities are. It's a new way of doing business. Actually being able to have very large entry vehicles changes the way that these payloads come into the atmosphere. We're looking at actually using HIADs, the Inflatable Decelerator technology, to recover launch assets, both first stage recovery as well as second stage. So that we're not really talking about these vehicles being the same shape that you would have coming into an atmosphere where you're delivering a payload, but actually maybe something a little bit elongated that conforms well to the launch asset that you want to recover, that gives it more of a gliding reentry or a gliding capability back to Earth.
Whether it's a fair expectation or not, those of us in the public have come to expect NASA and its partners to always come through with solutions to overcome challenges. The brilliant team working on HIAD has done just that. The ideas and processes they have developed have pushed through some big barriers and will almost certainly help us land on far-off places like Mars, while also being used back here in our own atmosphere on Earth. It just goes to show that virtually any technological issue can be overcome when you put the right team of people on the problem. And this is truly the right team.